The first rockets were used as propulsion systems for arrows, and may have appeared as early as the 10th century in Song dynasty China. However, more solid documentary evidence does not appear until the 13th century. The technology probably spread across Eurasia in the wake of the Mongol invasions of the mid-13th century. Usage of rockets as weapons before modern rocketry is attested to in China, Korea, India, and Europe. One of the first recorded rocket launchers is the wasp nest, fire arrow launcher produced by the Ming dynasty in 1380. In Europe, rockets were also used in the same year at the Battle of Chioggia. The Joseon Kingdom of Korea used a type of mobile multiple rocket launcher known as the Munjong Hwacha by 1451. The use of rockets in war became outdated by 15th century. The use of rockets in wars was revived with the creation of iron-cased rockets, known as Mysorean rockets, which was developed in Indian Kingdom of Mysore during the mid-18th century, and were later copied by the British. The later models and improvements were known as the Congreve rocket and used in the Napoleonic Wars. China. The dating of the invention of the first rocket, otherwise known as the gunpowder-propelled fire arrow, is disputed. The history of Song attributes the invention to two different people at different times, Feng Zhisheng in 969 and Tang Fu in 1000. However, Joseph Needham argues that rockets could not have existed before the 12th century, since the gunpowder formulas listed in the Wujing Zongyao are not suitable as rocket propellant. Rockets may have been used as early as 1232, when reports appeared describing fire arrows and iron pots that could be heard for 5 leagues when they exploded upon impact, causing devastation for a radius of 600 meters, apparently due to shrapnel. A flying fire lance that had reusable barrels was also mentioned to have been used by the Jin dynasty. Rockets are recorded to have been used by the Song Navy in a military exercise dated to 1245. Internal combustion rocket propulsion is mentioned in a reference to 1264, recording that the ground rat, a type of firework, had frightened the Empress Mother Gongsheng at a feast held in her honor by her son the Emperor Lizong. Subsequently, rockets are included in the military treatise Huolongjing, also known as the Fire Drake Manual, written by the Chinese artillery officer Zhao Yu in the mid-14th century. This text mentions the first known multi-stage rocket, the Fire Dragon issuing from the water, thought to have been used by the Chinese Navy. Rocket launchers known as wasp nests were ordered by the Ming army in 1380. In 1400, the Ming loyalist Li Jinglong used rocket launchers against the army of Zhu Di. The American historian Frank H. Winter proposed in the proceedings of the 20th and 21st History Symposia of the International Academy of Astronautics that southern China and the Laotian Community rocket festivals might have been key in the subsequent spread of rocketry in the Orient. Spread of rocket technology. Mongols. The Chinese fire arrow was adopted by the Mongols in northern China, who employed Chinese rocketry experts as mercenaries in the Mongol army. Rockets are thought to have spread via the Mongol invasions to other areas of Eurasia in the mid-13th century. Rocket-like weapons are reported to have been used at the Battle of Mohi in the year 1241. Middle East. Between 1270 and 1280, Hassan al-Rama wrote his al-Farushia wa al-Manasib al-Harbiya, which included 107 gunpowder recipes, 22 of which are for rockets. According to Ahmad Y. Hassan, al-Rama's recipes were more explosive than rockets used in China at the time. The terminology used by al-Rama indicates a Chinese origin for the gunpowder weapons he wrote about, such as rockets and fire lances. Ibn al-Badr, an Arab from Spain who had immigrated to Egypt, described saltpeter as snow of China. Al-Baytar died in 1248. The earlier Arab historians called saltpeter, Chinese snow, and Chinese salt. The Arabs used the name Chinese arrows to refer to rockets. The Arabs called fireworks Chinese flowers. While saltpeter was called Chinese snow by Arabs, it was called Chinese salt by the Iranians, or salt from the Chinese marshes. India. Mercenaries are recorded to have used hand-held rockets in India in 1300. By the mid-14th century, Indians were also using rockets in warfare. Korea. The Korean Kingdom of Joseon started producing gunpowder in 1374 and was producing cannons and rockets by 1377. However, the multiple rocket launching carts known as the Munjong Hwacha did not appear until 1451. Europe. In Europe, Roger Bacon mentions gunpowder in his Opus Majus of 1267. However, rockets do not feature in European warfare until the 1380 Battle of Chioggia. Conrad Kaiser described rockets in his famous military treatise Bellefortis around 1405. Jean Froissart had the idea of launching rockets through tubes, so that they could make more accurate flights. Froissart's idea is a forerunner of the modern bazooka. Adoption in Renaissance-era Europe. According to the 18th-century historian Ludovico Antonio Muratori, rockets were used in the war between the republics of Genoa and Venice at Chioggia in 1380. It is uncertain whether Muratori was correct in his interpretation, as the reference might also have been to bombard. But Muratori is the source for the widespread claim that the earliest recorded European use of rocket artillery dates to 1380. Conrad Kaiser described rockets in his famous military treatise Bellefortis around 1405. Kaiser describes three types of rockets: swimming, free-flying and captive. Jones de Fontana in Bellicorum Instrumentorum Liber described flying rockets in the shape of doves, running rockets in the shape of hares, and a large car driven by three rockets, as well as a large rocket torpedo with the head of a sea monster. In the mid-16th century, Konrad Haas wrote a book that described rocket technology that combined fireworks and weapons technologies. This manuscript was discovered in 1961, in the Sibiu Public Records. His work dealt with the theory of motion of multi-stage rockets, different fuel mixtures using liquid fuel, and introduced delta-shaped fins and bell-shaped nozzles. The name rocket comes from the Italian rocetta, meaning bobbin, or little spindle, given due to the similarity in shape to the bobbin or spool used to hold the thread to be fed to a spinning wheel. The Italian term was adopted into German in the mid-16th century, by Leonard Fronsberger in a book on rocket artillery published in 1557, using the spelling Rogit, and by Konrad Haas as Raket. Adoption into English dates to ca. 1610. Johann Schmidlapp, a German fireworks maker, is believed to have experimented with staging in 1590. Early modern history. Lagari Hassan Celebi was a legendary Ottoman aviator who, according to an account written by Evliya Celebi, made a successful manned rocket flight. Evliya Celebi purported that in 1633 Lagari Hassan Celebi launched in a 7-winged rocket using 50 akka of gunpowder from Sarayburnü, the point below Topkapi Palace in Istanbul. Sieminovich, Artis Magna Artilleriae Pars Prima, first printed in Amsterdam in 1650, was translated to French in 1651, German in 1676, English and Dutch in 1729 and Polish in 1963. For over 2 centuries, this work of Polish-Lithuanian Commonwealth nobleman Kazimierz Siemienowicz was used in Europe as a basic artillery manual. The book provided the standard designs for creating rockets, fireballs, and other pyrotechnic devices. It contained a large chapter on caliber, construction, production and properties of rockets, including multi-stage rockets, batteries of rockets, and rockets with delta wing stabilizers. Indian Mysorean rockets in 1792. The first iron-cased rockets were successfully developed and used by Tipu Sultan, the ruler of the Kingdom of Mysore, against the larger British East India Company forces during the Anglo-Mysore Wars. The British then took an active interest in the technology and developed it further during the 19th century. The Mysore rockets of this period were much more advanced than the British had previously seen, chiefly because of the use of iron tubes for holding the propellant. This enabled higher thrust and longer range for the missile. After Tipu's defeat in the Fourth Anglo-Mysore War and the capture of the Mysore iron rockets, they were influential in British rocket development, inspiring the Congreve rocket, which was soon put into use in the Napoleonic Wars. 19th-century gunpowder rocket artillery. William Congreve, son of the controller of the Royal Arsenal, Woolwich, London, became a major figure in the field. From 1801 Congreve researched the original design of Mysore rockets and started a vigorous development program at the Arsenal's laboratory. Congreve prepared a new propellant mixture, and developed a rocket motor with a strong iron tube with conical nose. This early Congreve rocket weighed about 32 pounds. The Royal Arsenal's first demonstration of solid fuel rockets took place in 1805. The rockets were effectively used during the Napoleonic Wars and the War of 1812. Congreve published 3 books on rocketry. Subsequently, the use of military rockets spread throughout the Western world. At the Battle of Baltimore in 1814, The rockets fired on Fort McHenry by the rocket vessel HMS Erebus were the source of the rocket's red glare described by Francis Scott Key and the Star-Spangled Banner. Rockets were also used in the Battle of Waterloo in 1815. Early rockets were very inaccurate. Without the use of spinning or any controlling feedback loop, they had a strong tendency to veer sharply away from their intended course. The early Mysorean rockets and their successor British Congreve rockets reduced veers somewhat by attaching a long stick to the end of a rocket to make it harder for the rocket to change course. The largest of the Congreve rockets was the 32-pound Carcass, which had a 15-foot stick. Originally, sticks were mounted on the side, but this was later changed to mounting them in the center of the rocket, reducing drag and enabling the rocket to be more accurately fired from a segment of pipe. In 1815 Alexander Dmitrievich Zasyadko began his work on developing military gunpowder rockets. He constructed rocket-launching platforms and gun-laying devices. Zasyadko elaborated a tactic for military use of rocket weaponry. In 1820 Zasyadko was appointed head of the Petersburg Armory, Okhtensky Powder Factory, Pyrotechnic Laboratory and the first highest artillery school in Russia. He organized rocket production in a special rocket workshop and formed the first rocket subunit in the Imperial Russian Army. Artillery Captain Józef Bem of the Kingdom of Poland started experiments with what was then called in Polish Rocka Kongrevska. These culminated in his 1819 report Notes sur les fusils incendiaires. The research took place in the Warsaw Arsenal, where Captain Józef Kosinski also developed multiple rocket launchers adapted from horse artillery gun carriage. The first Rocketeer Corps formed in 1822. It first saw combat during the Polish–Russian War 1830–31. Accuracy greatly improved in 1844 when William Hale modified the rocket design so that thrust was slightly vectored, causing the rocket to spin along its axis of travel like a bullet. The Hale rocket removed the need for a rocket stick, traveled further due to reduced air resistance, and was far more accurate. In 1865 the British Colonel Edward Monnier Boxer built an improved version of the Congreve rocket by placing two rockets in one tube, one behind the other. Early 20th-century rocket pioneers. At the beginning of the 20th century, there was a burst of scientific investigation into interplanetary travel, fueled by the creativity of fiction writers such as Jules Verne and H.G. Wells as well as philosophical movements like Russian Cosmism. Scientists seized on the rocket as a technology that was able to achieve this in real life, a possibility first recognized in 1861 by William Leach. In 1903, high school mathematics teacher Konstantin Tsiolkovsky, inspired by Verne and Cosmism, published The Exploration of Cosmic Space by Means of Reaction Devices, the first serious scientific work on space travel. The Tsiolkovsky rocket equation, the principle that governs rocket propulsion, is named in his honor. He also advocated the use of liquid hydrogen and oxygen for propellant, calculating their maximum exhaust velocity. His work was essentially unknown outside the Soviet Union, but inside the country it inspired further research, experimentation and the formation of the Society for Studies of Interplanetary Travel in 1924. In 1912, Robert Esno Peltery published a lecture on rocket theory and interplanetary travel. He independently derived Tsiolkovsky's rocket equation, did basic calculations about the energy required to make round trips to the Moon and planets, and he proposed the use of atomic power to power a jet drive. In 1912 Robert Goddard, inspired from an early age by H.G. Wells and by his personal interest in science, began a serious analysis of rockets, concluding that conventional solid-fuel rockets needed to be improved in three ways. First, fuel should be burned in a small combustion chamber, instead of building the entire propellant container to withstand the high pressures. Second, rockets could be arranged in stages. Finally, the exhaust speed could be greatly increased to beyond the speed of sound by using a de Laval nozzle. He patented these concepts in 1914. He also independently developed the mathematics of rocket flight. Goddard worked on developing solid propellant rockets since 1914, and demonstrated a light battlefield rocket to the U.S. Army Signal Corps only 5 days before the signing of the armistice that ended World War I. He also started developing liquid propellant rockets in 1921, yet he had not been taken seriously by the public. Nevertheless, Goddard reclusively developed and flew a small liquid-fueled rocket. He developed the technology for 214 patents, 212 of which his wife published after his death. During World War I, Yves Le Prieur, a French naval officer and inventor, later to create a pioneering scuba diving apparatus, developed air-to-air solid fuel rockets. The aim was to destroy observation captive balloons used by German artillery. These rather crude black powder, steel-tipped incendiary rockets were first tested from a Voisin aircraft, wing-bolted on a fast Picard Pictet sports car and then used in battle on real aircraft. A typical layout was 8 electrically fired Le Prieur rockets fitted on the interpane struts of a Nieuport aircraft. If fired at sufficiently short distance, a spread of Le Prieur rockets proved to be quite deadly. Belgian ace Willy Coppens claimed dozens of Drachen kills during World War I. In 1920, Goddard published his ideas and experimental results in a method of reaching extreme altitudes. The work included remarks about sending a solid fuel rocket to the Moon, which attracted worldwide attention and was both praised and ridiculed. A New York Times editorial suggested that Professor Goddard, with his chair in Clark College and the countenancing of the Smithsonian Institution, does not know the relation of action to reaction, and of the need to have something better than a vacuum against which to react. To say that would be absurd. Of course, he only seems to lack the knowledge ladled out daily in high schools. New York Times, 13 January 1920 and 1923. German Hermann Oberth published Die Rakete zu den Planetenroman, a version of his doctoral thesis, after the University of Munich had rejected it. In 1929, he published a book, Wedge zur Raumschifffahrt, and static-fired an uncooled liquid-fueled rocket engine for a brief time. In 1924, Tsiolkovsky also wrote about multi-stage rockets, in Cosmic Rocket Trains. Modern rocketry pre-World War II. Modern rockets originated when Goddard attached a supersonic nozzle to the combustion chamber of a liquid-fueled rocket engine. These nozzles turn the hot gas from the combustion chamber into a cooler, hypersonic, highly directed jet of gas, more than doubling the thrust and raising the engine efficiency from 2% to 64%. On 16 March 1926, Robert Goddard launched the world's first liquid-fueled rocket in Auburn, Massachusetts. During the 1920s, a number of rocket research organizations appeared worldwide. In 1927, the German car manufacturer Opel began to research rocket vehicles together with Max Valier and the solid-fuel rocket builder Friedrich Wilhelm Sander. These activities are generally considered the world's first large-scale experimental rocket program, Opel ROCKE, under the leadership of Fritz von Opel, leading to the first manned rocket cars and rocket planes, which paved the way for the Nazi-era V-2 program and US and Soviet activities from 1950 onwards. In 1928, Fritz von Opel drove a rocket car Opel ROCKE.1 on the Opel Raceway in Rüsselsheim, Germany, and later with the dedicated RAK-2 rocket car at the Avis Speedway in Berlin. In 1928, Opel, Valier and Sander equipped the Lippisch Entei glider, which Opel had purchased, with rocket power and launched the manned glider. The Entei was destroyed on its second flight. Eventually glider pioneer Julius Hatry was tasked by Fritz von Opel to construct a dedicated glider, again called Opel ROCKE.1, for his rocket program. On September 30, 1929, von Opel started at the Frankfurt Rebstock Airport with the Opel Sander ROCKE-1 airplane with himself as pilot, the world's first public manned rocket-powered flight, but experienced a hard landing. The Opel ROCKE program and the spectacular public demonstrations of ground and air vehicles drew large crowds, as well as caused global public excitement as so-called «rocket rumble», and had a large long-lasting impact on later spaceflight pioneers, in particular on Wernher von Braun. 16-year-old Werner was so enthusiastic about the public Opel ROCKE demonstrations, that he constructed his own homemade rocket car, nearly killing himself in the process, and causing a major disruption in a crowded street by detonating the toy wagon to which he had attached fireworks. He was taken into custody by the local police until his father came to get him. The Great Depression put an end to the Opel ROCKE program and Fritz von Opel left Germany in 1930. Emigrating first to the US, later to France and Switzerland. After the breakup of Opel ROCKE program, Valier eventually was killed while experimenting with liquid-fueled rockets as means of propulsion in May 1930, and is considered the first fatality of the dawning space age. Starting in the early 1930s, during the last stages of the Weimar Republic, German aerospace engineers experimented with liquid-fueled rockets, with the goal that one day they would be capable of reaching high altitudes and traversing long distances. The head of the German Army's ballistics and munitions branch, Lieutenant Colonel Karl Emil Becker, gathered a small team of engineers that included Walter Dornberger and Leo Zansen, to figure out how to use rockets as long-range artillery in order to get around the Treaty of Versailles ban on research and development of long-range cannons. Werner von Braun, a young engineering prodigy who as an 18-year-old student helped Oberg build his liquid rocket engine, was recruited by Becker and Dornberger to join their secret army program at Kummersdorf West in 1932. Von Braun dreamed of conquering outer space with rockets and did not initially see the military value in missile technology. In the mid-1920s, German scientists had begun experimenting with rockets that used liquid propellants capable of reaching relatively high altitudes and distances. In 1927 and also in Germany, a team of amateur rocket engineers had formed the Verein für Raumschifffahrt, and in 1931 launched a liquid propellant rocket. Rocketry in the Soviet Union also began with amateur societies. Foremost was the Group for the Study of Reactive Propulsion headed by Friedrich Zander and Sergei Korolyov. From 1931 to 1937 in the Soviet Union, extensive scientific work on rocket engine design occurred at the Gas Dynamics Laboratory in Leningrad, which was merged with GERD in 1933, bringing rocketry fully under government control. The well-funded and staffed laboratory built over 100 experimental engines under the direction of Valentin Glushko. The work included regenerative cooling, hypergolic propellant ignition, and fuel injector designs that included swirling and bi-propellant mixing injectors. However, Glushko's arrest during Stalinist purges in 1938 curtailed the development. Similar work was also done from 1932 onwards by the Austrian professor Eugen Sanger, who migrated from Austria to Germany in 1936. He worked there on rocket-powered spaceplanes such as Silbervogel. On November 12, 1932 at a farm in Stockton, NJ, the American Interplanetary Society's attempt to static fire their first rocket failed in a fire. In 1936, a British research program based at Fort Halstead in Kent under the direction of Dr. Alwyn Crowe started work on a series of unguided solid-fuel rockets that could be used as anti-aircraft weapons. In 1939, a number of test firings were carried out in the British colony of Jamaica, on a purpose-built range. In the 1930s, the German Reichswehr began to take an interest in rocketry. Artillery restrictions imposed by the 1919 Treaty of Versailles limited Germany's access to long-distance weaponry. Seeing the possibility of using rockets as long-range artillery fire, the Wehrmacht initially funded the VFR team, but because their focus was strictly scientific, created its own research team. At the behest of military leaders, Werner von Braun, at the time a young aspiring rocket scientist, joined the military and developed long-range weapons for use in World War II by Nazi Germany. World War II. At the start of the war, the British had equipped their warships with unrotated projectile unguided anti-aircraft rockets, and by 1940, the Germans had developed a surface-to-surface multiple rocket launcher, the Nebelwerfer, and the Soviets already had introduced the -132 air-to-ground rocket. All of these rockets were developed for a variety of roles, notably the Katyusha rocket. During the Second World War, Major General Dornberger was the military head of the Army's rocket program, Zansen became the commandant of the Peenemünde Army Rocket Center, and von Braun was the technical director of the ballistic missile program. They led the team that built the AGGREGAT-4 rocket, which became the first vehicle to reach outer space during its test flight program in 1942 and 1943. By 1943, Germany began mass-producing the A-4 as the Vergeltungswaffe II, a ballistic missile with a 320 km range carrying a 1,130 kg warhead at 4,000 km per hour. Its supersonic speed meant there was no defense against it, and radar detection provided little warning. Germany used the weapon to bombard southern England and parts of Allied liberated Western Europe from 1944 until 1945. After the war, the V-2 became the basis of early American and Soviet rocket designs. In 1943, production of the V-2 rocket began in Germany. It had an operational range of 300 km and carried a 1,000 kg warhead, with an Amitol explosive charge. It normally achieved an operational maximum altitude of around 90 km, but could achieve 206 km if launched vertically. The vehicle was similar to most modern rockets, with turbopumps, inertial guidance and many other features. Thousands were fired at various Allied nations, mainly Belgium, as well as England and France. While they could not be intercepted, their guidance system design and single conventional warhead meant that they were insufficiently accurate against military targets. A total of 2,754 people in England were killed, and 6,523 were wounded before the launch campaign was ended. There were also 20,000 deaths of slave labor during the construction of V-2s. While it did not significantly affect the course of the war, the V-2 provided a lethal demonstration of the potential for guided rockets as weapons. In parallel with the guided missile program in Nazi Germany, rockets were also used on aircraft, either for assisting horizontal takeoff, vertical takeoff or for powering them. During the war, Germany also developed several guided and unguided air-to-air, ground-to-air and ground-to-ground missiles. Post-World War II, at the end of World War II, competing Russian, British, and U.S. military and scientific crews raced to capture technology and train personnel from the German rocket program at Peenemünde. Russia and Britain had some success, but the United States benefited the most. The U.S. captured a large number of German rocket scientists, including von Braun, and brought them to the United States as part of Operation Paperclip. In America, the same rockets that were designed to rain down on Britain were used instead by scientists as research vehicles for developing the new technology further. The V-2 evolved into the American Redstone rocket, used in the early space program. After the war, rockets were used to study high-altitude conditions, by radio telemetry of temperature and pressure of the atmosphere, detection of cosmic rays, and further research. Notably the Bell X-1, the first manned vehicle to break the sound barrier. This continued in the U.S. under von Braun and the others, who were destined to become part of the U.S. scientific community. Independently, in the Soviet Union space program, research continued under the leadership of the chief designer Sergei Korolyov. With the help of German technicians, the V-2 was duplicated and improved as the R-1, R-2, and R-5 missiles. German designs were abandoned in the late 1940s, and the foreign workers were sent home. A new series of engines built by Glushko and based on inventions of Alexei Mikhailovich Isayev formed the basis of the first ICBM, the R-7. The R-7 launched the first satellite, Sputnik 1, and later Yuri Gagarin, the first man into space, and the first lunar and planetary probes. This rocket is still in use today. These prestigious events attracted the attention of top politicians, along with additional funds for further research. One problem that had not been solved was atmospheric re-entry. It had been shown that an orbital vehicle easily had enough kinetic energy to vaporize itself, and yet it was known that meteorites can make it down to the ground. The mystery was solved in the U.S. in 1951 when H. Julian Allen and A. J. Eggers Jr. of the National Advisory Committee for Aeronautics made the counterintuitive discovery that a blunt shape permitted the most effective heat shield. With this type of shape, around 99% of the energy goes into the air rather than the vehicle, and this permitted safe recovery of orbital vehicles. The Allen and Eggers discovery, initially treated as a military secret, was eventually published in 1958. Blunt body theory made possible the heat shield designs that were embodied in the Mercury, Gemini, Apollo, and Soyuz space capsules, enabling astronauts and cosmonauts to survive the fiery re-entry into Earth's atmosphere. Some spaceplanes such as the Space Shuttle made use of the same theory. At the time the STS was being conceived, Maxime Faget, the Director of Engineering and Development at the Manned Spacecraft Center, was not satisfied with the purely lifting re-entry method. He designed a space shuttle which operated as a blunt body by entering the atmosphere at an extremely high angle of attack of 40 degrees with the underside facing the direction of flight, creating a large shock wave that would deflect most of the heat around the vehicle instead of into it. The Space Shuttle used a combination of a ballistic entry and aerodynamic re-entry. At an altitude of about 122,000 meters, the atmosphere becomes dense enough for the aerodynamic re-entry phase to begin. Throughout re-entry, the shuttle rolled to change lift direction in a prescribed way, keeping maximum deceleration well below 2 gs. These roll maneuvers allowed the shuttle to use its lift to steer toward the runway. Cold War rockets became extremely important militarily as modern intercontinental ballistic missiles when it was realized that nuclear weapons carried on a rocket vehicle were essentially impossible for existing defense systems to stop once launched, and launch vehicles such as the R-7, Atlas, and Titan became delivery platforms for these weapons. Fueled partly by the Cold War, the 1960s became the decade of rapid development of rocket technology, particularly in the Soviet Union and in the United States. There was also significant research in other countries, such as France, Britain, Japan, Australia, etc., and a growing use of rockets for space exploration, with pictures returned from the far side of the Moon and unmanned flights for Mars exploration. In America, the manned spaceflight programs, Project Mercury, Project Gemini, and later the Apollo program, culminated in 1969 with the first manned landing on the Moon using the Saturn V, causing the New York Times to retract its earlier 1920 editorial implying that spaceflight couldn't work. Further investigation and experimentation have confirmed the findings of Isaac Newton in the 17th century, and it is now definitely established that a rocket can function in a vacuum as well as in an atmosphere. The Times regrets the error. New York Times, 17 June 1969. A correction in the 1970s. The United States made 5 more lunar landings before canceling the Apollo program in 1975. The replacement vehicle, the partially reusable Space Shuttle, was intended to be cheaper, but no large reduction in costs was achieved. Meanwhile, in 1973, the expendable Ariane program was begun, a launcher that by the year 2000 would capture much of the geosat market. Market competition. Since the early 2010s, new private options for obtaining spaceflight services emerged, bringing substantial market competition into the existing launch service provider business. Initially, these market forces have manifest through competitive dynamics among payload transport capabilities at diverse prices, having a greater influence on rocket launch purchasing than the traditional political considerations of country of manufacture or the particular national entity using, regulating or licensing the launch service. Following the advent of spaceflight technology in the late 1950s, space launch services came into being, exclusively by national programs. Later in the 20th century, commercial operators became significant customers of launch providers. International competition for the communications satellite payload subset of the launch market was increasingly influenced by commercial considerations. However, even during this period, for both commercial and government entity-launched COMSATs, the launch service providers for these payloads used launch vehicles built to government specifications, and with state-provided development funding exclusively. In the early 2010s, privately developed launch vehicle systems and space launch service offerings emerged. Companies now faced economic incentives rather than the principally political incentives of the earlier decades. The space launch business experienced a dramatic lowering of per-unit prices along with the addition of entirely new capabilities, bringing about a new phase of competition in the space launch market.